There are already so many amazing videos about the multi-hole problem on the internet, on YouTube, explaining how cleverly you can understand that you should actually change after the Monty opens up one door without an award behind it. But in this video, I will be presenting an approach that's quite boring compared to the others. This is the approach that is going to um, show with conditional probabilities and a Bayesian formula to show that you actually change. This is meant to be um, a great exercise to understand the Bayes rule and the conditional probabilities. So here we go. So many people know in the Monty Hall problem, you are given three doors and you choose one. There's only one award behind the three doors. Like, so previously, you know your to start with your chances of getting randomly the award is 1/3, and the host opens up one of the remaining doors. So you chose one, there remains two. One of the doors with a goat behind it, not an award. And you are left with the question, okay, now that you know this one, I opened this one. Are you going to keep on choosing the one that are you going to keep the one that you have previously chosen, or are you going to change? So there are several, as I mentioned, several videos that show us how that tell us that you should change. But in this video, I will be solving it like actually a math problem, right? So to say. So um, to begin, like we need to define some random variables, right? So like and as we move on, as we go defining and solving these random variables, we're going to understand some of the dependencies and independencies and the conditionals, right? So first, let's define S as let's define S to be the door that I select. S for select, right? So, whoops. Okay, so this is the door that I select. And obviously, since you don't have any psychic powers, this is just random. Like you select, and S is it can be either 1, 2, 3, and you can argue that it is just arbitrary. You don't know anything. And this is a word, and this is the door with a word, right? So um, that's a for award, and obviously, no one's messing up the game. It's like 1/3. It's also random, and at this point, you know that since you are the contestant, you don't know where the award, and you're just randomly choosing. You know, S is independent of A. At this point, you know. But before I move on to the next one, I'm going to say the Monty and this M, and this is the door that the host opens. Okay, so this is also M. This is also either 1, 2, 3, but this is the tricky part because the host knows the two things. Host knows A, where A is, and host has to wait for you to choose. So M is not so independent. So the distribution of M is obviously conditioned on the information of S and A. So I know for sure S is independent of A. So like we know that this is probability of SA is equal to probability of S times probability of A, right? So they are perfectly independent. We know that. And However, M is not like that. So the probability of M has to be conditioned on S and A. So we are talking about a probability distribution of M, probability of M, that's conditioned on S comma A. So we're talking about a probability distribution of M like this. And since again, we're assuming the Monty, the host, and this was an actual TV show, and there was no foul play except for the mathematical problem that the show has. The problem has M doesn't do anything. It is like the moment that it is conditioned on S and A, the choice of M is independent. So we are talking about a probability of M. So M can take either of 1, 2, or 3. And so we are going to condition this on these S and A. But since we know they have to condition on, so this is it's either 1 or 2 or 3. But this has to condition on S and A, right? So we need to calculate this like a table. So we are talking about this is almost like a table here, and this table has to be so here we are calculating. Let me see if I can highlight this thing. So we're doing this table here, and this is conditioned on S and A, and I know S and A can be 1 1, so meaning the award can be at 1, and you correctly choose 1 and 1 2 1 3 2 1 2 2 2 3 3 1 3 2 and 3 3. So these are all probabilities of the M. So now we are talking about a probability distribution like this, a conditional probability distribution. All right, so again, let's another attempt to understand what this table is doing for the pair of S and A conditions. What I select, where the award is, because we know they can be anything. The probability distribution of M being 1 or 2, the probability of M being 1, the probability of M being 2, given S is 1, A is 2. So this is so this should be this particular uh, table cell of this table can be interpreted as probability of M is equal to 3 given S is equal to 1 and A is also equal to 1. All right, so far so good. So I know if I was right, if I chose, if the award is 1 and if I chose it, obviously I know for a fact that it is not going to open up. So what from the policy that's M, let's fill up the easy ones on this table, right? So I know if I chose S, Monty is not going to open it up. There's no way, right? So like I chose it, and it's against the rules. Monty is not going to open it up. Similarly, if I chose 1, Monty is not going to open it up, and if Monty the host knows that it is at 2, Monty is not going to open the door 2, right? So similarly, Monty is not going to open up what I chose and the door. And we can fill out the zeros similarly, right? It's not going to open up where the door, where the award is, where I chosen the award, and so on and so forth. Do you all see how I fill the zeros? So these zeros are filled with the fact that Monty cannot open up either I chose it or where the award is. That's the definition by Monty. And everything else, Monty just randomly. This is the problem definition. Monty randomly opens up whatever remains, right? So he can open up out of these in this situation, in this first situation, since there are two doors to be opened, so he can open up with half probability. And in this situation, so this is one probability distribution that has to sum to one. This line, uh, every row has to sum to one because m can be 1, 2, or 3, conditioned on whatever it conditions on. That's the definition of the conditional probability. And there's only one chance for m to open and everything else, right? So I'm going to fill out whatever remains with whatever probability remains. So the probability distribution of, if I were to write probability of A equals 1 is 1/3. Probability of A equals 2 is also 1/3. Probability of A equals 3 is again 1/3. And similarly, you can see that probability of S equals 1 is equal to 1/3, or S equals to I is 1/3 for I equals 1 to 3, right? So we know, now we have an understanding of all of the probability distributions in this problem. So in order for me to decide on what to do, I have to understand, so I need to know that this game is symmetric, right? I could choose one. I can call it 1, let's say. I select 1 and Monty opens 2. Then I should calculate if I should move it to 3 or stay at 1. And similarly, the same problem, the same calculation, everything is symmetric. Everything remains if I choose 2, Monty chooses 3. Should I switch to 1 or stay at 2, right? You can all see that it is all the same. So my question then, which probability is higher? The probability that award is, let's not write the award first. Let's make the condition, right? So I choose 1 and Monty chooses 2, right? Again, I'm going to compare the probabilities of switching or staying, keeping, right? So probability of award is what? Condition on I chose and Monty opened 1. So this is the probability comparison that I need to make in order for me to choose switch. I have to see that the award, the probability of award being at 3 is greater than award as being at 1. This means I already hit initially, right? So this is I already hit, right? So this is I missed in the first place. So if this probability is greater, then I should change. And if this is greater, I should keep. And if they are the same, then it's just a game, right? I might as well keep, right? Or just, yeah, it is the game wants you to mistake that it is the same. You just, by changing or keeping, you're just introducing another excitement, but it's not. So notice that this is the probability of A equals 3 given S equals 1, M equals 2. So like this is something that we don't have, right? We have the conditional probability of M condition on A and S, but we don't have this. But the Bayes rule allows me to calculate this actually. So notice how I'm going to, let's write the Bayes rule first of all here. our good base rule here. I am interested in probability of A given B, but this is not directly available to me. What is available to me is probability of B given A and probability of A divided by probability of B. So this is our good base rule. And we call this guy posterior, and this is prior. So with the observation, so this is with the evidence, so this is my evidence, and this is my likelihood. With my observation, I would like to carry my belief about the prior, A, and make it into posterior. So what I'm going to do is I'm going to calculate an expression for this guy, which is normally very difficult to calculate. So I'm interested in this, right? So this is not available in any of our tables, but I would like to be able to calculate that. Notice I'm going to write it, but I would like to condition everything on s equals 1. I'm not going to touch this. This s equals 1, the game starts, actually, the probabilities, like the everything being changing, starts from you choosing s equals 1. So I'm not going to move that at all, right? So what I'm going to assume, first of all, I'm going to try to switch A and M, because probability of M given S comma A is available. That's the probability distribution of the host's behavior, but this is not readily available. So I'm going to change the space rule into something like this. So probability of A given B, instead of probability, I'm going to write it probability of A equals 3 given, now let me take a better color. So looking at this, I'm going to write what we are interested in. So we are interested in probability of A equals 3 given S equals 1, comma, M equals 2. And I would like to write the equal, and I'm going to write a huge division line. Let me delete this little part so that it gives me enough space to write. So notice that the conditional in after the vertical bar, there are two elements. The one good way to maneuver despite that is to ignore the fact that s equals 1 exists there. Meaning, keep the s equals 1 just behind the vertical at all times. So if that's the case, this one would be probability of, so I'm taking this 1, m equals 2 to the other side. So I'm interested in probability of m equals 2 given s equals 1 is always there. I'm going to keep it, comma, a equals 3. And this one, PA, what was A in this example? The one that I am trying to observe, probability of A equals 3. I'm not going to close the parenthesis yet because I have to keep it probability of S equals 1. Everything is conditioned on the same thing. And similarly, the numerator, the B, the one that I am interested in, but I cannot observe, is m equals 2. However, this has to be conditioned on s equals 1 as well. So this is what I am trying to do. And I'm going to compare this expression versus the other one. So I'm going to compare this. Again, let's write what I am interested in for our problem. Probability of m equals 2 given s equals 1, comma, a equals 3 probability of A equals 3 given S equals 1 divided by probability of M equals 2 given S equals 1 versus, or let me write, is it greater or less? Question. That's what I'm trying to find, right? And let's write the other one. So this other one is I'm trying to find if the probability of award being on the one that I had previously chosen is greater. So that's the one that I'm trying to find. So probability of Monty already chose S equals 1, A equals 1, probability of A equals 1, S equals 1, divided by probability of M equals 2, S equals 1. All right, things are getting simpler. First of all, I already have what I want to calculate. First of all, let's see that I don't have this, the denominator. I need to find it via um, total probability rule. And this is this like why would, first of all, I can take this red and I can eliminate it from both sides because they are both divided by the same thing, but I'm not going to do that. Like, for the sake of solving this problem, you can do that, but we are not interested in solving why I should be changing. So we're not interested in solving if I should be changing. We're interested in why I should be changing. And I'm interested in actually calculating these probabilities. So I'm going to go and write here, how would the probability of M equals 2 condition on S equals 1 pan out? So let's look at the M probability. So I know the probability of M is conditioned on S and A at the same time. But here, in this one that I'm interested in, there's no A. So A can be anything. So this figure in the denominator, probability of M equals 2 given S equals 1, has to include all the possibilities of A, right? So this is actually um, calculated with all the possibilities of A, sum over all possibilities of A, probability A equals A, probability of M equals 2 given S equals 1, comma, A equals A, right? So this is what I should be calculating, and it's the same number. Before I move on to that, let's go ahead and try to solve the upstairs. The first thing, our numerator, right? So the first thing that there are uh, there are so many probabilities that we need to fill in here. But the good news is, like, everything is there already. We have already um, intuitively established what is a what probability of M should be for a pair of S and A, pair of what I selected, what the host opened. So the thing that I wanted you to look at is this term. So probability of A equals 3 given S equals 1. So let's understand what this is. The probability of the award is on the third door, conditioned on the fact that I have chosen the door 1. So the fate is not playing a game with anyone. So we know that the award can be at anywhere, and you, since you are the contestant, you don't know where it is. Since they are independent, you know that this is probability of A equals 3. This is it, right? And you know that this is also probability of A equals 1. So initially, with the prior, there's no mistake that these two numbers are the same. We know that this is 1/3. And similarly, this is also 1/3. And one other thing that now it is time for me to look at the top, this thing. So since I'm interested in finding the m equals 2 S1A3, m equals 2 S1A1. So if A was supposed to be, if the award was supposed to be 1, and I chose it in the first place, what is the probability that M chooses the 2, something that has already happened, but with the likelihood, notice that this is the likelihood, and the whole thing is posterior, I am going to calculate the likelihood and multiply it with the prior, and normalize it with the evidence and find my actionable item, the best case scenario. So I'm going to go back and try to highlight the two lines that matter for me. So I know I'm trying to find the probability of S equals, what was I trying to find? Let's go. So I was trying to find M equals to S1A3, S1A1. So S1, S1A1. So I'm going to look at this line and S1A3. So this is the line, right? And from these lines, I'm interested in something that has happened, the probability that M equals 2. So I'm interested in these two things, specific to this thing and this thing. So what I'm going to go and write this thing, probability of M equals 2 given S1A1 and probability of M equals 2 given S1A3. So the first one in the next page is 1. So this is from the table. So this thing, let me take another color this time. What color? Let me take a nice blue here. So I know this thing is definitely 1. I know I didn't even need to look. If I chose 1 and if the award is at 3, there's only one chance for M to do, and that's 2. And similarly, if I hit it in the first place, this has to be health, right? So I guess it is almost happening. Let's go ahead and write. So 1 times 1/3 divided by, and I'm going to write the denominator in a second, greater or less, I'm questioning, 1/2, 1/3 divided by. I already know the answer. I don't need to look at the denominator. I can just eliminate this. I know with double the probability, the chances of it being on the third door, sorry, the it being on the third door is twice the probability or twice the likelihood that it being on the first door that I chose. But since we are interested in the actual probabilities, I would like to calculate the denominator, which is the same thing. So I'm going to do this sum. So for A equals 1, so for A equals 1, probability of A equals 1 is 1/3 times probability of M2 S1A1. That's the thing that I have already calculated. It is already 1/2. Plus probability of A equals 2 and probability of M2 S1 A2. He is never going to, he cannot, by the definition, he cannot open the door where the award is. So it's 1/3 times 0 plus, and the last one, A equals 3, that's again 1/3 times probability of M2 S1 A3, that was the part in the numerator, that's 1. And the same thing here, 1/3 times 112 plus 1/3 times 0 plus 1/3 times 1. And finally, I hope I have enough space. So when we sum all of them, this is 1/3, and this is 1/6. This sums to a half, and so the answer is on here is 2/3 greater, 2/3 is greater than 1/3. So this is the ultimate answer. So like in several videos, they close one of the doors. Oh yeah, the award is in this region, in this two-door period. So therefore you should change, they say. But now we walk through the math, how this 2/3 is calculated from the Bayesian perspective, and we have come to the conclusion that you should change. All right. So that was the most boring yet informative, not informative, but a good math solution of the Monty Hall problem.